Yeah, thanks for the nice words and the invitation. But it's always good to be back in Glasgow, and staying there for a week or two. I'm changing from my Norwegian accent to the Glaswegian accent, so but it takes more than one day, so I know what you're talking about. So I have a presentation. Yeah, here it is. Okay, thank you. I was given 20 minutes. I could probably spend more. So I'll try to be quick. So I'll be quick on some slides and would try to give the message. It was truly inspiring to listen to from the UN and talk about the ocean and in the future. And I guess that's why I'm here as well. I have 3 kids, and they will probably have more kids themselves. So that's why. We Norled, I've been lucky to work with Norled for couple of years now, and Norled is operating in car ferries and passenger boats in Norway. That's it. So it's a local brand. But I think what all you have seen is that in 2015 the transition from the diesel started in Norway with battery-driven ferries. So Norled developed the first battery-driven vessel. I think it's a ship in the world that was fully operated on batteries. This ferry is still operating, working fine. And what we've seen in Norway is the fuel transition from diesel-driven ferries to battery-driven ferries has been excellent. Next year will be around 80 such ferries, zero-emission ferries running on batteries. Batteries are wonderful, but they will only take you this far out of the port, in port. You cannot sail across the oceans on batteries because of the technology. So what we did in Norway, or the Norwegian Road Administration, which is really looking ahead, backed by the Norwegian government, is that okay, we need something else, and that something else was hydrogen. So in 2016 or 17, they started a process of developing the first hydrogen ferry, which was tendered in Norway. So all the big operators in Norway tendered for this, what is become Hydra now. And Norled won it. I've been with the project since day one. So we developed the tender, we developed the technology, we developed the ferry, and now the ferry is operating on batteries. It's sailing on batteries now. So we're going to install the hydrogen system now in the winter. We are, I have some more slides for this, but this is a sizable ship. It takes 80 cars, 300 passengers, sails with around 10 knots. So this is a ship, and I'll come back to a bit later on how we can use this technology also for different ship types. And as you see on the slides, that we have 400 kilowatt fuel cells on board from a company. We have a liquid hydrogen tank from Linde in Germany with a storage capacity of 4 tons. This is a pilot project. This is a demonstration project. This ferry can run 100% of batteries, no problem for that particular route. But the tender and the competition and this showcase is to demonstrate that this technology is scalable. And we are demonstrating this. The same technology, as you see in the picture here now, we are tendering currently for 2 much larger ferries, ocean-going ferries. We are in the middle of the tender process now. It's going to be decided by Christmas. And that's 2 big RoPax ferries, where we scale up from 4 tons on board to, say, 6 or 7 tons storage capacity, and to 4 megawatt of fuel cells on board. So with 4 megawatt fuel cells and 6-7 tons of hydrogen storage, you can sail in the North Sea, no problem. So that's basically where we're going, and as you see in the picture here, this is new technology development. We have developed a storage tank. We developed a fuel cell system with including ventilation systems for safety. So it's a whole new way of thinking on how to produce electricity on board a ship. But as always, we have learned from the car industry, etc. Hydrogen-driven cars are available. You can go to the stores and buy it. If it's Hyundai or Toyota Mirai, it's the same technology basically. I will not go into the details. I think you can read it in the screen yourself. But the thing with liquid hydrogen is you store it, of course, at low temperatures, but the pressure is low. We have done a lot of dispersion cases, safety studies, and so we have running through a really rigid process together with DNV and the Norwegian Maritime Administration to get a safe design for this. So just some facts about the project before I go a bit further and go into some of my personal opinions and some where Norled is going. But as you see in this picture, we have liquid supplied from Germany on trucks. This is not the future. We need to have local produced hydrogen for shipping. If you look at there are many projects in Norway that was working with compressed hydrogen, and that's really where you have the possibility to have local produced hydrogen serving smaller ships, serving say a fleet of ships, and this where with this the economy of scale is really coming into the picture. So the green picture, the green dot in the picture here is a Norwegian project where they are planning to develop a liquid hydrogen facility in Norway to supply ferries and high-speed passenger boats in Norway. And this Mongstad is close to Bergen, and there are like big companies like Equinor that is working to become a liquid hydrogen producer. The current capacity of liquid hydrogen production in Europe today is around 20 tons. For this 20 tons per day, that's the capacity. We are working with a tender for high-speed passenger boats in Norway, and only that small project in Norway will require something like 5 tons per day of hydrogen production, of liquid hydrogen production. So it's no question that the hydrogen supply chain is missing to serve the maritime world. And this is how we're going to do the liquid bunkering for the ferry. This is in the parking position, and this is how we will look like when we get there. This will be in March or April next year. Then it will look like this locally. This is in the Stavanger area. So we will have the truck from Linde coming from Germany, and we have a bunkering tower between the truck and the ferry for a safe transfer onto the bunkering tower. With ferries and passenger boats, it's important to have a short bunkering time because we earn money with sailing. So what you see in the picture now, it's about 1 hour bunkering time to empty the truck to get it across to the ferry. Of course, in the beginning we will spend some more time, but that's the target: 1 hour to empty that truck onto the ferry. So I was saying a little bit about the barriers. How can we take this technology, be it compressed hydrogen or liquid hydrogen that we are working with? What's missing? And basically, number one, we need a hydrogen supply chain. It's towards the maritime towards shipping is totally missing. So in Norway, they have taken up this, say, task. The Norwegian government is now laying out the plan. Okay, where should the bunkering hubs be? And there's a pre-projects running now. You see there are around 15 dots in the Norwegian map here, and these 15 places has been now financed for hydrogen production in Norway. There are some other private initiatives, so I think maybe 20 or 25 places are being targeted now for hydrogen production, more or less only to serve ships and shipping, and this be fish farming vessels, fishing vessels, cruise vessels, car ferries, high-speed passenger boats. So this is shaping up in Norway now. We have a 2, 3, 4 year advantage on, I would say, Sweden and Denmark, as we're always competing with. But it's quite nice to see the government now laying their plans for transition with new fuels towards shipping. So I think in the future you will see something like you see in the picture to the right. You will see dedicated terminals along the Norwegian coast, probably also along the Scottish coast for Calmac ferries, etc., where you have integrated production facilities together with bunkering facilities. And this is what's the task given. What can we do for this change? And this is the technology solution. And this could be compressed hydrogen or liquid hydrogen. There's no difference. We have the technology, and I think during the 3 days there, you will see lots of presentations saying, yeah, yes, we can do it, we are doing it. Then I'm an engineer, naval architect from Glasgow. So then I asked my friends that are working with the economics, so okay, how much will this cost? And as you said, yes, somebody has to say this is doable. So I'm saying hydrogen in the future will be low cost when we have mass production, when technology develops, when offshore wind is cheaper than the other energy sources. We can use offshore wind to produce hydrogen. And there are lots of projects now with offshore wind and hydrogen production where they use the offshore wind when the energy demand or electricity demand is low on the mainland, such as night. So we produce hydrogen at night to low cost. Scotland should be in a fantastic position to do this. And my belief is that, I think I also say that this low cost hydrogen will be cheaper than diesel before 2030. So this crossing point of these curves is around 2030 in my view. So, but how to get there before? We have this gap now where hydrogen is much more expensive than diesel. So in Norway we have an initiative, I think it's mainly driven by Wilhelmsen, which is the biggest ship owner in Norway. They say to the Norwegian politicians, we need a contract for difference to cover the gap between diesel and hydrogen now. And then with increasing diesel prices, with increasing CO2 tax, the price of diesel will go up. That's the red line. And the hydrogen price, the green line, will come down with mass production. If you look at solar electricity, solar panels, offshore wind, this is happening with technology development. I'm an engineer, so the politicians and the economics and the lawyers, they need to find out the mechanism. But this is a legal mechanism. The Norwegian government is targeting this now. So let's see. And I also see this as a topic of later in the conference in a day or two. So, and if Norled gets this legal document saying, okay, we will cover the gap between the diesel price and hydrogen price, then we can do many ship types. Not all of them. I'm stopping with some deep sea. But I'll show you a few cases later on that we've been working with. Because this is the conclusion. The old technology is ready. We have the fuel cells. The combustion engines are coming into place. The more advanced solid oxide fuel cells are coming within, I don't know, 5-10 years. And the storage solutions, we have it. So this is a matter of doing it on a naval architecture basis. And also on the regulatory side, safety, risk, alternative design, this is working. We are developing safe designs. It's all about engineers and safety engineers doing the tricks together. So I've been lucky. I've been leading this work. My background is risk and naval architecture. So I've been leading this work with the alternative design, where we develop safety and ship design together. So we find a good combination and a good solution in the end. So, and I guess you all follow the news. So this is a kind of a status of the news for the hydrogen ships projects in the world. There are more, many more, but just to show that we are at a point now where we have real demonstration projects, Hydra and the ferries in San Francisco. We have a transport vessel in between Australia and Japan being built, etc. And then it's lots of, say, projects in the making. I'll be fast now with the last slides, but this we can do on hydrogen, high-speed passenger transport, no problem. This is a project Norled is working with. We have developed this alongside with Hydra. So this will take passengers in 35, 40 knots, zero emission, safely. We're working on tenders with this also now. This we can do. This is typical short sea vessels in the North Sea, trading 2-3 weeks round trips. They stay 1, 2, 3 days in ports. They sail for 1 or 2 days between ports, often 12 hours, hopping around, delivering timber, coal, sand, rocks, different products, steel, aluminium, etc., going in a tramp voyages on the North Sea, visiting Norway every 2 or 3 weeks, and then continent, UK, Baltic Sea. These are sailing in 9-10 knots. With 2 of these liquid hydrogen tanks that we are putting on board the ferry, you can do this operation zero emission. We have the fuel cells, we have the storage. This is a doable project. I'll be more happy to do a new build with those ship types, but retrofitting can be some hassle. There are people working with retrofitting this, but for new build, this is doable. So this is coastal trade, short sea trade. And then we went to Stolt in Holland. Okay, can we do Atlantic crossing? We did a study with a student and 2 engineers in Stolt, myself and another engineer at the ship design office. Yes. Atlantic crossing, especially if you do the naval architecture trick here and you design this kind of ships with care and integrate the fuel systems in a better way than you see on this picture. This is a retrofit we looked at, and you see parts of the solution. We put these liquid hydrogen tanks on the deck and discussed a lot with Stolt. Oh, can we do it this way? Yes, we can do it. It's not the best, but let's just check it out. And the result is that doing it in a kind of practical way and retrofitting, you can say, do this Atlantic trading 70% zero emission. That was the, I think that was the result around on a hybrid mode. You will use then diesel or heavy fuel oil for 30%, but that takes you a long way, and that's retrofitting. New build, there shouldn't be any problem to do that towards 100% zero emission on the Atlantic crossings. So this was just to test the limit of the technology and how this in practical can do. So we take the Norwegian car ferries and Norwegian high-speed passenger boats. Okay, we tested in the North Sea. Yes, we can do that for most of the ship types in the North Sea, and also for Atlantic shipping, it's doable with some care. And that's why I think you are also interested in this. This is not 100% the solution, but it just to give you maybe some motivation and to show that yes, shipping can go towards zero emission. So we can do it. Cost too high today, and the hydrogen fuel supply chain is totally missing. So that's two big hurdles: technology, safety, and these engineering things we can do. Thank you.
Thanks, Ivan. I was really keen to see that graph of the pricing, and I think, you know, the point you make about a carbon tax is coming, and I think most ship owners these days, if you listen to any ship owner, they're talking more and more about a carbon tax needing to come in to level the playing field. So I was pleased that you answered that. I think the point you made about it being scalable, you know, 6 to 7 tons of hydrogen going on board, 4 megawatts of fuel cells, and for a North Sea trip, that's great, because that's where that's beyond starting. That's actually into the implementing. I think that's fantastic. I'll just say that don't forget that propulsion is not the only source of fuel consumption on board a ship. There's an electrical generation component as well. And in my case, on a tanker, 20 to 25% of my emissions is for electrical generation. And I need 600 kilowatts of electrical generation to provide enough electricity to run the ship. 600 kilowatts is completely doable. So I can reduce my emissions by 20 to 25% by deploying technology that's available today with simply a little modification, really. I mean, you're not talking about a complete propulsion system modification, you're talking about electrical plant. So it is doable, it certainly is. Maddie, I believe the electricity in the room today is powered by a fuel cell.
Yeah, it's got hydrogen and fuel cells outside. So, yeah.
Okay, so the power that we're seeing around us here today is actually coming from a hydrogen fuel cell. So I think that's an important point to celebrate, because it's certainly the first time I've been in a room that fuel cells and hydrogen has been used. I see a table of young people over here. You guys aren't going to get away lightly. I'm going to be coming to you for some questions, because I'm pretty sure that the fossils in the room have got 1 million questions, but you guys will probably have 10 million. So I'm going to be coming to you. So there'll be questions, there'll be the opportunity to ask questions. I think for those online, there is a system of raising questions, but I will be coming around the room, so don't be shy. And I don't need eye contact. I will point you out by way of your look or by way of your interesting sort of posture. So hopefully everybody in the room is fully engaged and listening. We talked a lot about the hydrogen supply chain. And now Stephen is going to come up and tell us a little bit about his solution for the hydrogen supply chain. So Stephen, over to you.
Thank you very much. Hello. Yeah, there we go. Thank you, everybody. Welcome to COP26. You've all made that really long journey here, and it's amazing to see everybody in this room and the buzz of the whole climate and the world watching us. And as much as it's been a long journey for all of you perhaps to be here, it's also been a long journey for us to be here also. and I'd like to tell you a little bit about our journey and how we've got here. So today, we're looking to showcase the world's first liquid hydrogen bunkering facility. We're here in this South Rotunda here, and we did a lot of work to try to get our unit into the Malin Group. It was a struggle, and unfortunately, because of the security issues, we weren't able to do that. But fear not, the facility is actually on its way. It's on its way to the Scotland Enterprise Technology Park, and on the Friday, we will actually be showcasing this at the City of Glasgow Centre, the Riverside campus. And so for those of you who are actually available on the Friday and would like to see the facility up close, you're more than welcome to come and take a look and come and contact me, and we'll definitely get you in this fantastic event. So I'd like to talk about the technological evolution of technology, because we recognize that to get people onto the mindset to get towards zero emissions by 2050, we need to bring some people along on that journey. And we recognize that hydrogen, yes, is expensive, yes, there are challenges, and yes, there are some people probably here in this industry at the moment that still believes that, for example, fossil fuels are the way to go, bunker fuels, even those people that think that maybe LNG is a transition fuel. And you know, we can't demonize these kind of people, because admittedly, we have been in the LNG industry for the past decade or so. And actually, our technology here today has evolved from that. And what we want to do is to show that whilst we have had our interest in LNG and the decades of experience in that, that we should not put all our efforts into focusing on that. We should focus on what we know and how we can actually use that knowledge to do better. And so back in 2015, we actually built the UK's first ever LNG bunkering facility for a project for Shell. And this was quite innovative at the time. But again, this was 6 years ago. We've taken a lot of learnings from that, and then we moved forwards. And in 2017, we actually then delivered a more refined version of that technology for Singapore, who actually at that time was also looking to improve on their technology as well, because this was very novel for them. And we also have to recognize there are many countries around the world where maybe the challenge for the energy transition is actually more challenging than in other places, and that climate change actually is disproportionately affecting places around the world. And we cannot sort of think that we could sit on our high horse and say, yes, we'll do zero emissions, but not bring people along. So that takes us today. And today, as I say, hopefully we'll be showcasing some information about our world's first liquid hydrogen bunkering facility. And maybe the next stages after that is to investigate the liquid to compressed gaseous hydrogen bunkering facility. So this was our project back in 2015. And as you can see from the photograph here, our infrastructure is very, very small. This footprint is probably no more than a little over a metre wide or so, probably about by about half a metre or so. And I think a lot of people, when we talk about infrastructure, a lot of people think that infrastructure is very, very expensive. But maybe because they're having this thought that ships are big and therefore infrastructure needs to be big. But here we're actually suggesting, no, actually we can actually do this thing with very, very little infrastructure. And you can see there in the background the vessel here. I think there was about 200 cubic meters worth of tanks on this vessel, 100 meters long, 2 vessels coming about twice a week, and taking up to about 50 tons a time through this small little system. Then we refined that technology. Here, this was a project we delivered for Singapore, and whilst in the first case, it was a simple truck that would connect to the system and use that system to then deliver to the ship. In this project, we actually managed to build a facility that was even smaller, but was able to connect up to 2 tanks at a time to allow continuous bunkering process without a stop, start, and disconnection. And also, we managed to integrate a lot of the key safety features as well, including breakaway couplings, gas detection, a lot of the safety features that you'd actually expect to have for a proper fueling system that isn't just in a demonstration mode. And here it brings us to 2021. This is a glimpse of what you'll hopefully get to see for those of you that will be coming on Friday, if you're able to make it. Of course, we would have liked to have shown you the full thing here to this audience today. But again, you can see the very, very small footprint of this unit, about 2.5 meters long by about 1 meter and a bit wide. And you'll see there that there's a big pump in the middle, which will be delivering the fuel to the ship, which is ultimately the big engine of our system, but also a control system to match that as well. And this is just the beginning. So in terms of the architecture of this facility, we see it as 2 strands. So right now, we're looking at bringing in liquid hydrogen from containers, either as an ISO container or perhaps through a road transport truck. And the big box in the middle shows the different pathways to be able to deliver either liquid hydrogen as a fuel to the ships or compressed hydrogen. So if you look at the bottom line with the purple line, you'll see that we have a pump, a centrifugal pump system, which ultimately will then deliver liquid hydrogen. And as we go forwards and we develop our technology forwards, we're looking at this new system where we'll actually take liquid hydrogen from a truck and we'll high pressure pump that, we'll then gasify that and deliver high pressure compressed hydrogen, all in the same box. So let's talk a little bit about the technology involved in our World First project. So we've decided to select a liquid hydrogen centrifugal pump, and the size that we picked was something of the order of 500 litres per minute. It's a 4-stage pump, and it's got 3 connections. So there's 1 connection for the tanker to connect into, 1 for the offloading of the fuel into the ship, and also a vapor return line in case we need to sort of manage some of that vapor pressure and boil off and other aspects like that. And then another key feature of the infrastructure is the coupling. So again, in order to be able to share this information, we understand that there are 2 different types of couplings. So the 2 dominant ones are both the Linde coupling, which is a proprietary design from Linde, but there's also a coupling which is also called the Air Force bayonet. And we believe that actually that is derived from the American Air Force, because for many, many decades, liquid hydrogen has been used in rockets and sending rockets into outer space since the 1960s, in fact. And so what we want to actually say is that this technology is not new. It's been around for decades. And all we're doing is just reusing what has been existing, well-tested, and putting it into a different application. Also to share with you that the convention of these couplings are that usually the male connector is on the hose side and the female connector is on the plant side. And we're also working in terms of standards and regulations to make sure that we've got compatibility and that we're all working on the same page. We have to talk about safety. So our system also contains pre-alarm systems and breakaways. And again, these are systems that are typically mandated now, or there are international standards in terms of having these systems. And so ordinarily there'd be a breakaway system. So in case the ship drifts away, it will separate in a safe way with the 2 ends closing. But before that actually happens, there's a pre-alarm system, which means that if the ship starts to drift away, we can already detect that is happening. And there's a 2-level approach up to a 3-level approach to be able to do that. Then, of course, we have the mass flow meter. So our selection of choice is a Coriolis mass flow meter. And this is a fantastic unit, which is extremely accurate and is able to measure both the liquid and the gaseous vapor at the same time. Due to the vibration of the tubes, it is able to do it more accurately than many other conventional meters. And if anybody is wanting to understand custody transfer and ensuring that they get every drop of fuel into their vessel, then they can do so with this meeting. So now it takes us to the next steps. What are the next steps? We're all here today at this COP26 conference because we all want to be a melting pot of ideas. We all need to put our ideas together and see what we can do. And one of the issues that we need to think about is how do we go about scaling up the hydrogen liquefaction? As Ivan had mentioned earlier on, in Europe today, there is probably about 20 tons per day liquefaction capability. And what's very interesting when we put our press release out, maybe sometime in July of this year, that we started to receive some inquiries. One such inquiry, for example, was an organization that was looking to design a vessel, and they said to me, is it possible to have some 16 tons of liquid hydrogen per day for our single vessel? I said, yeah, that's a very interesting size, some 3/4 of what Europe is able to produce today. So something radically is going to have to change if we'd like to think that maybe there would be 10 vessels of this thing. And if, let's say, there are 10 vessels, let's say there's 160 tons per day required, that's going to mean we're going to have to really scale up the hydrogen liquefaction. And maybe the economics will change if we consider these possibilities. And one such an example of this is the scaling up of the import and export technology. We can't think that maybe, some countries are better suited than others, perhaps to produce green hydrogen. And this example pilot project is one that we understand is happening between Japan and, yes, Australia as well. And some will say it's not green hydrogen. But we can see the scale that we're going through. I mean, this vessel here, I believe, can take up to 1,250 cubic meters of liquid hydrogen. And this is only a very small, this is the start. And we understand that companies like Kawasaki are building even larger vessels that will get to the same size of those that we expect already of LNG. And finally, collaboration. Again, I think today it's going to be a fantastic discussion. We've got all the people that we need in this room. COP26, let's make things happen. We're not here today to sort of just speak words and pander to sort of what the politicians do. Let's let them do that. But here as the industry, we are the ones that are driving change. So let's get down to business and make sure we can deliver what we need to do. Thank you very much.
I read when I was reading up a little bit about you that you're very involved with the British Standards Institute. So you're helping to actually develop the standards that the industry will be operating to. And I think that's tremendous, that not only are you just participating in the facilitation of hydrogen, but you're also at the table around standards. I think that's tremendous. I was really interested to hear about the couplings and the technology that's behind the couplings. And is that something that you think you yourselves will be, you'll be outsourcing, I presume, in terms of manufacturing? But will that be something you need to patent?
So there are two aspects of it. So those couplings that I showed there, they are vacuum insulated bayonet couplings. And usually those couplings are the ones that are used to connect between the road tankers to the actual system. One of the things that hasn't yet been defined is the connection to the ships. And again, there's a few different organizations that are looking at developing different couplings. And I'm sure as the industry comes together, we'll start to progress and we'll start to come to some agreement as to what those couplings might look like.
Ivan, you have the floor? Yes. Can we have Ivan's microphone switched on?
Just a comment to you. We are working with exactly the same coupling, so it's really nice to see. Maybe the company is called Mantech, so it's good to, and they're working together with Linde. So there's the same philosophy, vacuum insulated male-female coupling. So that's I think you should talk to them also for your standardization purposes.
Sure.
And I was really pleased that you both spoke about safety. And I think, to be quite frank, in the language of what's going on out there in the industry, there's a lot of impetus and focus on, the need to reduce emissions. We get that, we agree with that, but it has to be done safely. I was really pleased that both of you picked up on that point. And you also talked about the Australian hydrogen manufacturing, about it not being green. And I think that you made a really good point there, because I think we could get bogged down in the whole discussion around the array of colors behind hydrogen. And that's not for this session. We're not here to debate the difference in colors. We're here to talk about the technology application. And I think the color of hydrogen will determine itself as the demand rises. And as the cost comes into question, there will be a natural evolution in that area. So I was really pleased that you made that point. City of Glasgow College, Friday afternoon, all-day event. Okay, great. Well, now we're leading into Kristofer. And when I was doing a little bit of research on Kristofer ahead of the event here, I picked up something rather interesting. And Kristofer was working on a project, and he said we were always able to make the customer feel that they had a competent and committed partner at their side. And I think that's a lot about what we're talking about here today, is a sense of partnerships. That it's not only people working in independent areas of the business, but it's the partnership between the supply side and the consumer side. And I thought that was a really great point that was made in something that you put together on the net. But you also are no longer a component supplier, but a solution provider. And I think that's great because, again, this is what we're looking for. We're looking for solutions, and we're here today to do a workshop around the application of solutions. Now, you did mention that the customer's idea on price were another issue. So we can't escape the price debate, but Kristofer, the floor is yours.
So thank you for having me here. My name is Kristoffer Lorentsson. I'm working for MN Energy Solutions, and I'm here today to talk to you about the technology of a liquid hydrogen fuel gas supply system. So just briefly, wanted to show you how I ended up here. So I work for a company called MN Cryo. We belong to the MN Energy Solutions Group since 2016, but our company was founded already in 1908. And we have been working with cryogenic engineering since 1956, so that's 65 years today. We're located in Gothenburg, Sweden, and previously we have 60 references for marine LNG projects, but we also have for land-based applications previous experience of more advanced cryogenic liquids such as liquid hydrogen and liquid helium, where we have provided both land-based stationary storage tanks as well as transportable containers for liquid helium. So with those two different technologies, we now have the possibility to combine them into a marine liquid hydrogen fuel gas supply system. So what do we mean? What is a fuel gas supply system? So we consider this to be all the equipment that is placed permanently fixed on board the ship in order to receive liquid hydrogen from a trailer or a shoreside bunkering facility, to store that liquid in a controlled way in a storage tank, vaporize it, heat the liquid up to gaseous form so we can supply gaseous hydrogen to a consumer. This consumer might be a fuel cell, but it could also potentially be an internal combustion engine running on pure hydrogen. So the fuel gas system contains of a bunker station to receive the hydrogen. It contains of vacuum insulated piping to distribute the hydrogen into the storage tank. On the end of the tank we have what we call the tank connection space. This is a closed off area which you do not normally enter, where we have our vaporization equipment, all of the safety equipment such as valves and all of the core process components that is needed. It also combines with the external skid called the heat exchanger unit, which is driving the heat transfer into our vaporization systems inside the tank connection space. So this component or this equipment, the function of it is to supply hydrogen to the consumer at the correct temperature and pressure. So the design principle for a liquid hydrogen fuel gas system is that we receive hydrogen transported into the pressurized storage tank. We store the liquid hydrogen inside the tank at a slightly higher pressure than what is needed at the consumer. So if we have a supply to a fuel cell that requires 3.5 bar gauge pressure, inlet pressure, we store this liquid slightly higher than that. So we store it in liquid form at minus 253 degrees inside the tank at 4 bar gauge. So this overpressure is the driving force behind the process. So we press the liquid through the vaporizer. It's at 4 bar gauge. So we just have a phase transition from liquid form to gaseous form. So we heat the liquid up from minus 253 degrees minus all the way up to 20 plus degrees. So we can distribute it in gaseous form to the consumer, which could be a fuel cell or a combustion engine. What happens now when we take liquid out of the tank? Then the internal pressure of the tank will slowly decrease. So to prevent this, we have an additional vaporizer circuit called pressure buildup unit, also working with vaporization. So we take liquid out of the bottom of the tank, send it through this pressure buildup unit, vaporize it, and send the gas back on top to prevent the pressure loss inside the tank. So we can always control the pressure. And if the pressure under any circumstance would be too high, we can take gas directly from the top of the tank, just send it through the vaporizer, just heat it up. So there's always a way to control your pressure, which is the driving force behind this process. So there are no pumps or rotating equipment inside this core technology of a liquid hydrogen fuel gas supply system. It's all driven by pressure. So it's very robust and reliable. No rotating components, no maintenance. So the only rotating equipment that is inside is we need some kind of a heat source in order to get the vaporization process going. So the fuel cell generates a lot of heat. It needs to be cooled. So we can take the energy of the cooling circuit from the fuel cell, exchange that in a heat exchanger unit that heats up an internal circuit. It's the blue circuit, which is a closed loop of a mixture of glycol and water to add heat into our hydrogen vaporizers. So the main purposes of this system is to contain and store cryogenic liquid, hydrogen, to contain the liquid and gas safe from surrounding environments. We don't want any gas leaks where it's not supposed to be. It's supposed to preserve liquid temperature low, maintain pressure below the max allowable relief valve setting, and to maximize your holding time. And the holding time is basically all the time you can put liquid hydrogen in these tanks without needing to venting off in order to release anything through your safety relief valves. So this is done with vacuum technology. So with our tank solutions, we have a design where we have an inner vessel that is containing the liquid. This inner vessel is placed inside another vessel, which we call the vacuum jacket. Both of these vessels are of austenitic stainless steel, which is the most suitable steel for these kind of low temperatures. So the liquid is stored in the inner tank. Between the inner and outer tank, we have evacuated all of the air, so it's a vacuum space combined with multi-layer insulation. The liquid is transported from the tank into the TCS, tank connection space, where we have the vaporization. And from the vaporizer, we can submit it to the consumer through double wall piping. So inside the TCS, which is our battery limit, we either protect the environment by having the piping vacuum insulated or inerted with nitrogen, and I will elaborate on how this works. So in order to never have any leak and exposure of gaseous hydrogen to the environment, because this is an explosive and dangerous gas if you don't treat it right, all the piping is either vacuum insulated or pressurized with nitrogen. So if you have a vacuum insulated double wall pipe, we have an inner pipe that transfers the media. The if this pipe were to leak, the leakage will not go into the air, it will go into the second pipe, which is covering outside. This pipe will be directly lead off the gas to the vent mast with the purging of nitrogen. And you purge with nitrogen in order to avoid having any oxygen enrichment, because if you have oxygen, you can have an ignition. And the other way where we are in the phase where we transport hydrogen in gaseous form to the consumer, we have an outer wall that is pressurized with nitrogen. So if we have a leakage in the inner pipe there, we have a pressure indicator that detects that the pressure in the outer pipe will drop, and therefore we can, with this detection, have an emergency shutdown of the system. So under no circumstances will you have any type of leakage in your surroundings where you can have an ignitable source. So the safety philosophy is that this is a volatile gas. We need to avoid exposure, so we work with this double wall piping. All of the hydrogen can be detected and set off an alarm, so we can have an emergency shutdown in a safe manner to avoid any leakages, and all of the leakages will be routed to the safe area, and the only safe area on board the ship is the vent mast. There are some alternative gas supply methods that we need to look into for future projects. In the future, we see internal combustion engines as an alternative to fuel cells. This needs to be driven with a higher pressure. So for that we could potentially use a hydrogen pump that is installed in our tank connection space in order to raise the pressure to the needed level. Additionally, we can see the use of a gas compressor. Gas compressors also raises the pressure of the gas before we send it to the consumer, but they are raising the pressure in the gaseous phase. And a benefit of this technology is that this will also enable an improved holding time of the storage tank itself, because the gas compressor can handle the boil of gas that is generated in the tank and consume it. So you can have an internal holding time of your system. So what is the status of MAN Cryo today? We have delivered our first system in 2021. We have obtained the class approval from Lloyd's Register for this project, and from before we already have a preliminary approval in principle from DNV. And we have also this year initiated our first contacts with Classing Society Arena. Our hydrogen tanks are available today in sizes from 50 up to 300 cubic meters of LH2. I think that corresponds to 2,000 up to 15,000 kilo of liquid hydrogen content. We also have a pre-study to upscale the tank sizes all the way up to 600 cubic meters, and the preliminary results looks promising. So with this portfolio of tanks, we see that we can cover the market demand for a foreseeable future with this technology. Thank you.
Thanks, Kristoffer. Mandy, I'm sure you're going to tell us it's coffee time.
No, it's not coffee time. What it is now we've got a few minutes left for Mark is going to lead our presenters in a bit of a panel discussion and a bit of Q&A. We want to hear some questions from you, and I think we've got about 25 minutes before it's 40. We've got. I'll give you the sign when it's time to go to the coffee, but you just take it from there. Okay, thanks very much.
Thanks a million. Thought that was really interesting, but what I was interested in was on the energy to heat up the liquid hydrogen. You said that's coming from the fuel cell. Does that presume that it works with a high temperature fuel cell, and what would the effect be with a low temperature fuel cell?
We don't need more than 25, 30 degrees as an input from this. So we don't need any vast temperatures.
Great. And I think that's one of the important things to look at is the overall efficiency of the systems. And I was glad you brought that in, because I think any calculation that anyone's doing is looking at the the net energy absorption of a system to understand the total process efficiency that we're talking about. And of course, that ultimately determines the cost of operating in a hydrogen mode. So I promised I was going to come to the young people's table with a question. So what is it? And can you just, kind of give us an idea, who are you, who are you representing? And I particularly want the young people here to voice up, because I think it's important we hear from you.
Can you hear me? Yeah. Okay. Hello, everyone. We are fifth-year students from the University of Strathclyde. And we are here, firstly, to see your discussions and find out more, and partly because we're working on a fifth-year project. And it is looking into using hydrogen and alternative fuels for propulsion. So my first question would be for Ivan. It's kind of oddly specific, but I noticed that in your ro-ro vessel, the hydrogen tanks are all above and external. So I was wondering if you could comment on where kind of that comes from and why exactly they are external and so high up, considering the stability trade-offs that would have. Thank you.
If I get some sound, yeah. It's when we started this project many years ago, no rules, no guidance, nothing. So we put them on the roof because we didn't know how to handle any leakages and also the heat, or basically the coldness. If you have a puncture in the tank, you lose vacuum, you get a huge heat load onto your deck and your surroundings. So, but by putting this up in the open air, we're able to handle these say emergency situations. And now, after many years, we see that maybe we can put them down into the ship. But I'm not too comfortable with that yet, due to the heat loads and the dispersion cases from the process system, because if you have a leakage in your process system that's the piping going between the tank and the fuel cells, you need to get that out of your vent mast. And this, as you see from Mancruo, they have a nitrogen purge to minimize the risk of internal explosion, which is one way of doing it. Otherwise, you can dimension your pipe to withstand internal explosions, which we have done. We have an inherent safe design. So these are technicalities, and I'm happy to help you in your thesis. If you have Evangelos and Dimitris, and your professors have my contact details, so I can assist you, because this is a long discussion. But yes.
Yeah. Okay, we would be definitely interested in talking some more then. Thank you.
Great. Thank you. Great question. I see Michael Parker in the audience. Michael, if I could come across to you. Obviously, you're one of the original architects of the Poseidon Principles, and have for years now put a lot of effort into where the finance and banking community come to engage with ship owners and encourage, sometimes by stick and sometimes with carrot, to change. What are your thoughts? I'm not sure if you heard the whole panel, but what are your thoughts on hydrogen within the Poseidon Principles?
Can I also say Paul Taylor, my vice chair of SocGen, is also here, and we're both speaking tomorrow. What was very interesting listening to this, and I'm afraid I missed the very beginning, is it sounds like you're much further down the road than some of the big CEOs and ship owners tell us in private. And we had the Global Maritime Forum Summit last week, where we talked about how we're going to make the sort of step change. So on the one hand, this is very encouraging, because it sounds like the technology, as we've heard, is there. And of course, the big question is how are we going to finance that into the bigger scale we need for what I call international shipping. I didn't dare ask the size of the tanks you're talking about, but I don't know what size tank you need for a 23,000 TEU container ship or a very big ship. And I think what we think should happen is the scaling up through smaller shipping, whether it is coastal or inland or whatever, is going to be where this technology all gets tried and tested and proven, at the same time as obviously people are working on other different fuel solutions. So for this period, we're going to be dealing with multiple choices, and you see it in some of the orders being placed by major ship owners. I think, from what I heard last week, ammonia seems to be the fuel of choice at the moment, but that's simply because you can't scale up hydrogen yet for the big ship. So what Paul and I are very interested in listening to is this sort of technology, and of course the challenge is how we bridge the sort of venture capital type financing to what we do normally, which is finance big ships. But we're interested to listen, and frankly it has to get financed in order to accelerate the reduction in emissions or speed up the pathway to zero emissions. Great.
And Paul, would you like to add a comment?
Well, as usual, there's not usually too much to add to what Michael says, but I think we'll talk tomorrow about the Poseidon principles, but as signatories, we need to finance hydrogen vessels. It's the only way we'll align our own portfolios with what we've committed to and be in line with the IMO. But I will share Michael's thoughts about it. It was a really, really interesting presentation, and I was not only interested but very impressed by what you're doing. What I'd be very interested to hear more about is what your views are on the larger vessels, and we're hearing about 2030. Shipping banks really want to finance some of these larger vessels. That's the only way we're going to align our own portfolios. So how close is your technology to being able to be used on the larger vessels? You talked about crossing the Atlantic on 70% zero carbon. I mean, when will that be available, do you think, from a safety perspective and all the other areas? Because that was super interesting.
Would you like to answer?
I think this is the kind of huge question for the big ship or big ships, what to do. It's you have the ammonia debate. Ammonia supply chain is building up with the huge projects. It's easier to handle liquid ammonia. It's like minus 32 degrees and the low pressure, but still you need the independent tank, as we have with LNG and liquid hydrogen. You need an independent tank structure on the ship to store it. So, and with ammonia you have the NOx and the N2O gases that, in my personal view, is not in the debate at all. They just left it because ammonia is giving the is fixing the carbon issue nicely. I think my answer to this is, when people ask me, is that okay, the same. Why don't you use batteries? Yes, we use batteries when we can in Norled for the short routes with the low energy demand. And I think my answer to the hydrogen issue is also, I think I will use hydrogen as much as we can, because you need green ammonia and then you need to go via green hydrogen. So by any means, the hydrogen will have more or less the same cost as green ammonia in the future, and when everything comes together. So the cost issue, I think, will be the same. The fuel efficiency, ammonia engine, I don't know, somebody say 40%, some say 50%. Fuel cells they are starting now at 50%, will improve, especially with the high temperature cells. There will be 60–65% efficiency. So there's an issue you need to look into. And I think this is also a long discussion, but I'm always pointing to, I had a reference to Hydrogen Europe study. It's open on the net. It's a huge study they've done on behalf of EU Commission. It was presented in the summer, I think. And I have a map showing that how they see compressed hydrogen used, how they see liquid hydrogen used, and how they see ammonia used. And the answer to the big Maersk container vessels, that's ammonia, because there's so huge energy demands. But there's something in between there, and we don't know today. I think in 2030 you will see where the borderlines are. But for certain, as I showed, there's just some simple case studies, not too much work into. We see that we can take the hydrogen technology that we are proving for Norwegian car ferries now, and at least for North Sea operation, hydrogen can be done. And also this Atlantic crossing, as you see. So, I think the ship owners need to live with that the future will be different fuels, and maybe different fuels within their fleet for different ship types. So it's a big issue to find the right thing now. And I would also like to point out too that all these deep sea ships, nearly all of them are working with reducing the energy consumption needed, using for example sails and rotors, so and hull efficiency. So there's been a lot of studies into this, and for example, with not too much investments, they can reduce the energy consumption with 30%. So that's for free.